Hello, this is chapter 21, book problems. I'm going to restrict myself to 1 minute per slide so that the presentation does not completely put you to sleep. So it'll be approximately 54 minutes. So some of the slides I'll have to go over very quickly, and others might seem like they'll never end. And some I'll hit just perfectly. Have a pencil paper ready, a calculator. There will be some mathematics to do. Make sure you prove each slide. I will embed some extra credit as we proceed through the presentation, worth anywhere from 5 to 20 points depending upon the extra credit. Tweet me, and the first one who tweets me will receive the extra credit. Let's begin quickly. What is the connection between temperature and kinetic energy? Kinetic energy is the energy of motion. Motion causes collisions. Temperature is the indication of the number of collisions. How many degrees are between the melting point of ice and boiling point of water on the Celsius scale, on the Fahrenheit scale? Celsius, it's 100, 0 to 100. Fahrenheit, it is 32 to 212, so that's 180. What does 2 liters of boiling water, why does 2 liters of boiling water not have twice as great a temperature as 1 liter of boiling water? Because its average temperature of each molecule, it's going to be boiling at that, and we'll talk about that more next chapter. Why is it incorrect to say that matter contains heat? Heat is the flow of energy. When you take internal energy and you externalize it, that's the heat. In terms of differences in temperature between objects in thermal contact, in what direction does heat flow? Hot to cold, high energy to low energy. What is meant by saying that a thermometer measures its own temperature? Let's wait on that, and let's take that on the next slide. What is internal energy? Well, that's the grand total of all energy in a substance. What is the difference between a calorie, small c, and a calorie, large c? 1,000 scientific calories, small c, equals 1 dietary calorie, large c. What is the difference between a calorie and a joule? 4.18 joules per 1 calorie. So let's talk about number 6, and we'll continue it on the next slide. It has to do with thermal equilibrium. When the thermometer is sitting in hot water, I take a cold thermometer, room temperature, and I put it in very hot water. The cold thermometer will have generally lower area region of heat, and the heat will flow from the hot fluid into the thermometer, heating the thermometer. The thermometer in the water will reach a thermal equilibrium, and the energy will be, there won't be a difference. There won't be a difference in heat concentration. At that point, all the temperatures should be the same, and the temperature of the thermometer will be the same as the temperature of the hot fluid. Thereby, the temperature is taking the temperature of itself because of the concept of thermal equilibrium. Next, as I wait briefly, here we go. What does it mean to say that a material has a high or low specific heat capacity? High specific heat capacity means that matter can contain a lot of heat. Storage of heat means that it takes a lot of heat to change material 1 degree Celsius. So water is 4.18 joules per gram degree Celsius. Iron is 0.45. So the iron can contain more heat. The water can contain more heat as higher specific heat capacity. Do substances that heat up quickly normally have high or low specific heat capacities? They have low ones. How does the specific heat capacity of water compare to that of other substances? It is uncommonly, unbelievably, uniquely very high compared to all substances. Water is a very strange substance. Why is the North American West Coast warmer in winter months and cooler in summer months? Excuse me. The east coast of the United States, well, the ocean gives energy to the air above it in the winter, which is then carried over the land, warming it in the summer. The water absorbs energy from the air above it, and the cooler air moves over the land and absorbs energy from it. Something that the problem doesn't really say is that in the northern hemisphere, weather moves from west to east. So the water is west of California, say, and it will move west to east. And that's why you have palm trees in San Francisco, which has the same latitude as Washington, D.C. And because it doesn't really freeze very much, and if it does, it really doesn't freeze the ground terribly. So you can have the palm trees, which really you can't freeze the root ball. Why does a bimetal strip curve when it is heated? Because of the differences in the coefficient of thermal expansion. Coefficients of thermal expansion are specific to an individual substance. Solids and liquids have intensive, characteristic physical properties, one of which is the coefficient of thermal expansion, either volume or linear. And brass has considerably higher thermal expansion than iron, and the brass will curve more, so it'll curve in that particular fashion because brass has a higher coefficient of thermal expansion. Which expands most for increases in temperature, solids, liquids, and gases? Well, gases obviously will expand more. Their molecules are very, very, very far apart compared to liquids and solids. However, the thermal expansion is only characteristic for substances that are solids and liquids. That's very important. At what temperature is the density of water greatest? At 4 degrees Celsius. The density is approximately, when we say 1 gram per cubic centimeter, or 1,000 kilograms per cubic meter, that's about the density of water at 4 degrees Celsius. That's water at its most dense, and less than 4 degrees it expands, and greater than 4 degrees it expands. Ice is less dense than water because of its open crystalline structure. But why is water at 0 degrees Celsius less dense than water at 4 degrees Celsius? I'm not going to get into this. It says because there's a presence of microscopic slush. The best way to answer this is that it's by definition. If you look at the graph, I'll show you a graph in a little bit. It's by definition. When you get less than 4 degrees Celsius, water is less dense, and greater than 4 degrees Celsius, water is more dense. Why microscopically? I don't particularly care. Why do lakes and ponds freeze from the top down rather than from the bottom up? Because the ice water and ice are less dense and float on the surface. I'll get a little bit more specific about that in a little bit. Why do shallow lakes freeze quickly in winter and deep lakes not at all? All water must first be cooled to 4 degrees Celsius before a body of water can completely freeze. See, when the water, let's say the water is all 20 degrees Celsius and it cools at the top. Well, that cooler water is more dense and it's going to sink. So it's not going to go degree by degree. It's not going to say, well, I'll wait for the top layer to become 19 degrees and then fall. It'll fall in micro layers, and it creates this convection, the stirring up of the lake, and it will continue to stir and it will continue to fall until the entire lake is 4 degrees Celsius. We'll talk about this more in a little bit, but the whole lake has to be 4 degrees Celsius for it to actually ultimately freeze. Four plastic foam soup bowls contain the same amount of water as 20 degrees Celsius. You dunk cylinders of different metals but of equal mass in the bowls. All four cylinders have been in a hot oven and have the same temperature. Rank the bowls according to the maximum temperature of the water after the cylinders have been added. Heat transfer in calories is given by QmC delta T, where m is the mass in grams, c is specific heat capacity in calories per gram degree Celsius, and delta T is degrees Celsius. Well, perhaps it would have been better to put the tables of specific heat capacities next. But what I'll do is, I read the problem, and I'll show you the picture here. So you have A, B, C, and D, copper, aluminum, steel, and silver, respectively. And so let's agree. How do you really answer this? Well, the one that has the greater specific heat capacity will hold the most energy, will hold the most heat. So that should be what we're going to base this on. So the substance with the greater specific heat capacity will be first, and then the one with the least specific heat capacity will be last. So let's look at the specific heat capacities as are listed in the table in the following slide. Okay, so we find that in the table, aluminum is 0.9 or 0.215. I suppose they're using calories. And then what else? Copper is 0.092. That's considerably lower. Steel is 0.107. So it would probably be aluminum, steel. Copper is 0.092. Silver is 0.056. So I'm going to go with aluminum, steel, copper, and aluminum, steel, copper, and silver. So it will be aluminum, steel, copper, silver. And the order, if you remember, the aluminum is B, the steel is C, the copper was A, and the silver is D. And that's exactly what it is. So the order in which it will be B, C, A, D. It will be the substance with the highest specific heat capacity, aluminum, then iron, then copper, and then silver. So silver has the lowest specific heat capacity here, and aluminum has the greatest. Okay, now let's talk a little bit about the next problem before it actually gets there. Well, you know what? Let's go back and talk a little bit about the water. You're going to get this convection of the lake, and the water will cool off and fall, cool off and fall, cool off and fall until it reaches 3 degrees, and then it'll float because it's less dense than water at 4 degrees. We'll go back to that in a minute. Calculate the number of calories of heat needed to change 500 grams of water by 50 degrees Celsius. Can't do more than just what's there. It's going to be MC delta T. See, the book uses the equation MC delta T, M delta TC, same thing. And 500 times 1 calorie per gram degree Celsius times 50. And the next one would be times 30 times 1 times 500 would be 15,000 calories. So notice that the specific capacities are given in calories per gram degree Celsius, so that's what I have to use. I have to use grams for mass and degrees Celsius for temperature, and pretty straightforward. You're measuring Q, which is heat. Q stands for quantity of heat. It doesn't make a lot of sense maybe, but that's the way it is. Okay, next problem. A 30-gram piece of iron is heated to 100 degrees Celsius and then dropped into cool water where the iron's temperature drops to 30 degrees Celsius. How many calories does it lose to the water? The specific heat capacity of iron is 0.11 calories per gram degree Celsius. Well, the temperature change is 70 degrees, so it'll be 70 degrees times the mass of 30 times 0.11, and that's going to come out to 231 calories. I will let you know before you take the quizzes whether or not the signs are important, whether or not it's exothermic or endothermic. And that'll be based on, actually the sign is based on a temperature change. So that would be negative 70 because the final temperature is 30, so it'd be 30 minus 100 would be negative 70, so it would be negative 231. Suppose a 30-gram piece of iron is dropped into a container of water and gives off 165 calories in cooling. Calculate the iron's temperature change. You're simply taking Q equals M delta Tc, and you're just simply rearranging that equation to solve for delta T. So it's going to be delta T equals Q over MC. Again, the book in these problems generally uses calories per gram degree Celsius. In class, we generally use either kilograms per kilogram degree Celsius or sometimes kilojoules. So you just have to keep your wits about you in terms of what constant you're using. And you're solving for the change in temperature. You don't have to worry about negative or positive. Is it TF minus TI, whatever, just delta T. What mass of water will give up 240 calories when its temperature drops from 80 to 68? So that's a drop of 12 degrees. So again, you're rearranging the equation, M equals Q over C delta T, and that's 20 grams. And then when a 50-gram piece of aluminum at 100 degrees Celsius is placed in water, it loses 735 calories of heat while cooling to 30 degrees Celsius. Calculate the specific heat capacity of the aluminum, and it would be 0.21, which is approximately that's the range of specific heat capacities for metals. That's approximately correct. That would be a metal. Metals are generally in that area. Okay, so these are very simple problems. We'll get a little bit more complicated as we get a little bit later on. Okay, in your room there are things such as tables, chairs, people, and so forth. So which of these things has a temperature lower than the room temperature, greater than the room temperature, equal to the room temperature? Which is greater, an increase in temperature of 1 degree or 1 degree Celsius or 1 degree Fahrenheit? 29A, none lower than air temperature. Living things are more, inanimate things are the same. Celsius degrees are 9/5 larger. So that would be pretty straightforward with that. Let's talk a little bit about the Celsius degrees as being 9/5 larger. This is the derivation of the equation in the upper right hand corner of Fahrenheit temperature equals 9/5 degrees Celsius plus 32. So you'll see that there are 180 degrees between 32 and 212 for Fahrenheit. There are 100 degrees between 0 and 100, okay, freezing and boiling, freezing and boiling. So the Celsius degree, the individual Celsius degree would be larger, and it's actually 9/5 larger. How do you know it's 9/5 larger? Well, that's the slope. So the slope, 180 over 100, so it's going to be 1.8 a greater, or 9/5. If you drop a hot rock into a pail of water, the temperature of the rock and the water will change until both are equal. The rock will cool and the water will warm. Does the same principle hold true if the rock is dropped into a large lake? Yeah, the principle is true. Absolutely true. Of course it's true. But the changes in temperature will be extremely negligible. The temperature of the sun's interior is about 10 million degrees. 10 to the 7th is 10 million. Does it matter whether this is degrees Celsius or Kelvin? Defend your answer. No. A difference of 273 in 10 million is insignificant unless you're insistent on using 8 or more significant figures, which would be absurd. So with a number that large, 10,273 is not particularly important. Which has a greater amount of internal energy, an iceberg or a cup of hot coffee? The iceberg, I don't even want to get into it. It's absurd. This is not about heat. This is about internal energy. So the iceberg is enormous. If you take a bite out of hot pizza, the sauce may burn your mouth while the crust at the same temperature will not. Crust has a very low specific heat capacity. Water has a much higher specific heat capacity. The sauce is mostly water, and you are literally immersing, even though water doesn't conduct energy very well, you are immersing your lips into the water. So that's a little bit different. The pizza sauce has a higher specific heat capacity than the crust, and that would be the end of that. Right. Next. In the old days, on a cold night, it was common to bring a hot object to bed with you. Which would be better, a 10-kilogram iron brick or a 10-kilogram jug of hot water at the same temperature? The hot water would be unbelievably better because it can hold a tremendous amount of heat. So an iron brick, God, would hold a tenth of the amount of heat. In addition to overall motion of molecules that is associated with temperature, some molecules can absorb large amounts of energy and in the form of internal vibrations and rotations of molecules themselves. Would you expect materials composed of such molecules to have high or low specific heat capacities? High specific heat capacities. That's like water. That explains water to a T. Desert sand is very hot in the day and very cool at night. What does this tell you about the specific heat capacity? Very low, about a fifth of that of water. So sand is going to cool off very quickly. The specific capacity, of course, is listed right here. Why does adding the same amount of heat to two different objects not necessarily produce the same increase in temperature? Because specific heat capacities are different for each substance. When a 1 kilogram metal pan containing 1 kilogram of cold water is removed from the refrigerator and set on the table, which absorbs more heat from the room, the pan or the aluminum? The pan or the water? Well, the pan is probably made of aluminum, and aluminum has a much lower specific heat capacity, so the water will absorb more due to the higher specific heat capacity of the water. On a hot day, you remove from a picnic cooler a chilled watermelon and some chilled sandwiches. Which will remain cool for a long time? Which will remain cool for a longer time? The watermelon, it's watermelon, it's a lot of water, so it will maintain a constant temperature longer. Why is it important to protect water pipes so they don't freeze? Because water expands when it freezes, and that will literally pry the pipes apart. If you go into your basement, you might find a lot of your pipes insulated. They may be water pipes, hot water pipes, and you want to insulate those. There might be plumbing pipes that are hot. You want to insulate those. But you also want to insulate pipes that have any water in it because you don't want them to freeze. So you can inspect that. in your basement. Iceland is so named to discourage conquest by expanding empires. That's actually a true story. It is not covered with ice. It's not covered with ice at all. The average winter temperature of Iceland is considerably higher than regions at the same latitude in eastern Greenland or central Siberia. Why is this? Because it's surrounded by water. And water, like the Hawaiian Islands. Why are the Hawaiian Islands always at 72 degrees? Yet they're in the tropics because they're surrounded by water. And water maintains its temperature better. So that's a pretty easy question. You're going to be noticing probably a similar theme throughout this whole thing, that water is a pretty special, we're celebrating water a little bit, it's a very special molecule, and these are why. Because it can even control weather, so it's pretty intense stuff. A metal ball is just able to pass through a metal ring. When the ball is heated, thermal expansion will not allow it to pass through the ring. What would happen if the ring, rather than the ball, were heated? Would the ball pass through the heated ring? Does the size of the hole in the ring increase, decrease, or stay the same? Well, it would expand, like a jar of aluminum lid on a glass jar of mayonnaise. Glass doesn't expand very much, and aluminum expands a lot compared to the glass, and it just pries it right off. What is the difference between this ring and a lid? The lid has sides to it. It's a ring. Just one side of the ring is closed, but it's still a ring. Same exact thing. Exactly the same. Not similar, exactly the same. After a machinist slips a hot, snugly fitting iron ring over a cold brass cylinder, the ring becomes locked in position. It can't be removed, even by subsequent heating. This procedure is called shrink fitting. How does it occur? Can you conclude anything about the thermal expansion rates of iron and brass? Yes, brass will expand much more than the iron. Once the iron is on and shrinks back to its room temperature, you can't reheat the ring. You'll see in the next picture. They're connected. So if you heat the ring, you're going to heat the brass. If you're going to heat the iron ring, you're going to heat the brass, and you can't heat the ring in isolation because they're connected, and they will, heat will flow by conduction. So if I try to heat the ring, it will expand, but the brass will expand to a greater degree. So the answer is going to be obvious. Again, this is called shrink fitting. When you take a ring which has a small coefficient of linear expansion, and you put it over a substance of greater thermal expansion, then you get this shrink fit, and it's permanent. You have to literally cut the iron ring off the brass in order to separate them. So it's pretty stable. Next. When the iron is heated, it expands, but the brass expands more, preventing the iron from cooling. This is a extra credit problem. I want to know an industrial application. Be specific. The best answer and the first answer will receive the extra credit. So it might not be the first answer I get, but it will be the best answer I get within a reasonable amount of time relative to the first answer. So an industrial application of shrink fitting relative to metals, some kind of industrial application that would be familiar to us, not something strange, but something common, a common industrial application. Now the next problem is very similar to the ring, expanding. You should be able to do this. Suppose you cut a small gap in the ring, as shown. If you heat the ring, will the gap become wider or narrower? Well, what do you think? Well, what do you think based on what we've been doing with the ring, you know, the shrink fitting and everything else? So what's going to happen to the gap when I heat this? Interesting. Give it some thought, and let's see if we can get. You would not necessarily know the answer to this because you haven't really seen any films, nor have I spoke about this in class. So it'll be interesting to see whether or not you get a little bit of a closed in a gap, and the rest of it will expand. Well, it's wider, just as if the gap were filled with metal, it would expand. So this can be a little bit confusing, expansion. And remember, the expansion is a function of the specific metal or liquid that's involved. Again, gases do not have specific linear expansion or volumetric expansion for individual gases such as chlorine and bromine, etc. 1 liter of bromine, 1 mole of bromine, 1 mole of chlorine at room temperature is 22.4 liters. 1 mole of oxygen is 22.4 liters at STP, same thing. So it's going to be the same volume. And if I heat it, it's going to heat the same, expand the same. Would a bimetallic strip function if the two different metals happen to have the same rates of expansion? Is it important that they expand at different rates? Explain. No. It wouldn't. And yes, it is important. And one side must expand or contract more than the other. Otherwise, it's not going to work. Like a thermostat at home. Cite an exception to the claim that all substances expand when heated. Water. Below 4 degrees, water expands when cooled. An old remedy for a pair of nested drinking glasses that stick together is to run water at different rates into the inner glass. Well, we're going to skip that one. State whether water at the following temperatures will expand or contract when warmed. Well, if it's 0, I'm going to contract, and it's going to become more dense. At 4 degrees, it's going to expand. When it reaches higher than 4 degrees, and 6 degrees, higher than 6 degrees, it will expand. Suppose that water is used in a thermometer instead of mercury. If the temperature is at 4 degrees Celsius and then changes, why can't the thermometer indicate whether the temperature is rising or falling? Either cooling or heating at 4 degrees Celsius is ambiguous, completely ambiguous. Let's take a break. Okay, welcome back. If water had a lower specific heat capacity, would lakes be more likely or less likely to freeze in the winter, and why? More likely, less energy would be absorbed by the surrounding for each degree of cooling. Because let's say the water, instead of 1 calorie per gram degree Celsius, is 0.1. So it would have to lose far less heat in order to drop a degree. So, hey, it would be very likely to freeze. The ocean in New Jersey could very well freeze. Off the coast of New Jersey could freeze very easily, depending on how much lower the specific heat capacity of the water was. The next slide shows two graphs that you should be familiar with, at least one that you're definitely familiar with, the bottom one, where volume is on the y-axis, and if you have a given volume of water, it's shrinking as you get towards 4 degrees Celsius and expanding when you're colder than 4 degrees Celsius in the liquid form and warmer than 4 degrees Celsius. And that's true if you just turn the graph upside down and you're comparing density with temperature. It's going to be most dense at 4 degrees Celsius. When we say 1,000 kilograms per cubic meter or 1 gram per cubic centimeter, that's generally considered 4 degrees Celsius, depending upon the number of significant figures that you're going to rely on. How does the combined volume of the billions and billions of hexagonal open spaces in the crystals in a piece of ice compare with the portion of ice that floats above the surface of the water? Combined volume of all open spaces, same as the volume of ice above water. And that should be pretty consistent with our study of fluid dynamics. When ice freezes, you're kind of making like little life preservers in there. You know, you're trapping air in the structure of the water, if you think of it that way. So those spaces will actually help it float, and all those volumes together are going to equal the volume above the water. All those hidden volumes in the ice. People in the pioneering days placed hot potatoes in their pockets on cold winter days to keep their hands warm, assuming that a potato is mostly water. Andrew calculates 24,000 calories of heat are released by a 350-gram potato that cools from 85 degrees Celsius to 15 degrees Celsius. Alexis calculates that 102,000 joules of heat are released. Whose answer do you agree with? Well, obviously, it's 102,000 or 24,500. Agree with both, I guess, but actually the second one would be correct. Alexis is really the winner, although the answer in the book says agree with both, but whatever. My grandfather used to tell stories about putting hot potatoes in your pockets, walking to school in the morning. Kind of weird. If you wish to warm 100 kilograms of water by 15 degrees Celsius for your bath, how much heat would be required? Well, it's just going to be Q equals MC delta T, which is actually the same as Q equals M delta TC, same thing. Notice that you're going to have it in calories per gram degree Celsius. So it's going to be 1,500 calories times 4.18 is 6,276 joules. So it's the same value. It just kind of looks different, but the conversion is 4.18 joules per 1 calorie, or 4.186 joules per 1 calorie. So pretty straightforward altogether. Anthony's thin plastic water bottle holds 500 milliliters of water at temperature 28 degrees Celsius. He puts it into the refrigerator. Show that the refrigerator removes 50,000 joules of heat from the water to cool it to 4 degrees Celsius. So you're going to have a change in temperature of 24, 1 calorie per gram degree Celsius, 500 grams, 1 milliliter is 1 gram, and that's going to be 12,000 calories, or times 4.18, 50,000 joules, same value. Not very difficult altogether, pretty straightforward. We're getting towards the end here. We have several more problems left, but pretty straightforward. Again, it's Q equals MC delta T. And next problem is Samantha decides to try the ice water diet. She drinks water at 0 degrees Celsius and it must warm up to her body temperature of 37 degrees Celsius. How much ice water must she drink to burn 3,500 calories? That's the approximate energy content of a pound of fat. That's 3,500 kilocalories. That's one capital C is larger. Each calorie is 1,000 calories, so do the calculation. 95 liters of water, little weird. Why would she recommend or not recommend this diet for losing weight? Because this is around 400 glasses of ice water a day. So not a good diet. Not a good diet. A great problem though, but not a good diet. What would be the final temperature of a mixture of 50 grams of 20 degrees Celsius water and 50 grams of 40 degrees Celsius water? This is actually a good problem. You know that the calculation, the MC cancels. Let's just make this quick. The MC cancels, and you're left with TF minus T final minus 40 equals the additive inverse of T final minus 20, and then it's going to be T final is going to be 30. So kind of a cool problem. Just understand that the masses and the specific heat capacities will cancel out, which makes the problem a little bit more, a little easier to do. The next problem, 58. What would be the final temperature if you mixed a liter of 20 degrees Celsius water with 2 liters of 40 degrees Celsius water? Again, the C's cancel. Let's just do the math. You put 2m to make the m's cancel. So the answer is 33.3. Great problem. Make sure you can do the math. See if that problem, remind me in class. I'll do that problem in class. It's a really good problem to do. Just a note, the reason you have 2m as opposed to just m is because it's 1 liter. It says mix a liter with 2 liters. So, to make it equal. And then the M and the C will cancel. What would be the final temperature if you mixed a liter of 40 degrees Celsius water with 2 liters of 20 degrees Celsius water? Same idea. It's going to be, look on the right, it's going to be 2M, 2MC, and the M's and the C's cancel. Don't forget that additive inverse there. And you come down to 26.7 degrees Celsius. I'll do these problems on the board and I'll make those, I'll try to find problems on the problem set 11. If not, I'll do problems right out of the book. Good problems to do, actually. Very good problems to do. Really demonstrates your understanding of algebra. So the final temperature is 26.7 degrees Celsius. Right. Just a few more problems left. Next, what would be the final temperature when 100 grams of 25 degrees Celsius water is mixed with 75 grams of 40 degrees Celsius water, and the C's cancel, and then you just simply reduce everything else. There is, I think, a mistake here. No, I just had forgotten the parentheses. I forgot the parentheses there. But that'll come out to 31.4 degrees Celsius. So just make sure the C's cancel. And that's an easy one. That's number 60. And the next is going to be, what will be the final temperature of 100 grams of 20 degrees Celsius water when 100 grams of 40 degree Celsius iron nails are submerged in it? The specific heat capacity of iron is 0.12 or 0.11. It depends on the, what book you look the constant up in. We've done problems like this. You're solving for TF. Just keep your wits about you. You're going to come down to 20.9. The temperature should be between the two temperatures, so it should be between 20 and 40. If you don't deal with the additive inverse sign, then you're going to get a value probably less than what you should get. So that's a nice little trick. So you'd get an answer less than 20 degrees Celsius. What is the specific heat capacity of a 50-gram piece of 100 degrees Celsius metal that will change 400 grams of 20 degrees Celsius water to 22 degrees Celsius? So the specific heat capacities, what is the specific heat capacity of a 50-gram piece of 100 degree metal that will change 400 grams of 20 degrees Celsius water to 22 degrees Celsius? So the answer is 0.205. Very, 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 very straightforward problem. Very straightforward problem. So it'd be 0.205. Looks like possibly aluminum. Next problem, 63. Taylor finds that a certain amount of heat raises the temperature of a sample of iron by 10 degrees Celsius. Show that the same amount of heat will raise the temperature of an equal mass of lead by 35 degrees Celsius. Again, what you want to do is plug in to the values to notice making the ratio of the iron to the lead, and the answer will be the temperature change of the lead will be 35 degrees Celsius. Very straightforward problem. Just, again, keep your wits about you relative to all of your subscripts, etc. Suppose that a metal bar 1 meter long expands 0.5 centimeters when it's heated. How much would it expand if it were 100 meters long? Well, it's all proportional. 0.5 is to 1 as x is to 100, and it would be 50 centimeters. The linear expansion of metals is a direct linear relationship. It is a direct linear relationship. So it would be 0.5 centimeters over 1 equals delta L over 100. And solving for delta L, that's going to equal 50 centimeters. Okay. Next, 65. Steel expands 1 part in 100,000 for each Celsius degree increase in temperature. If the 1.5 centimeter main span of a steel suspension bridge had no expansion joints, how much longer would it be for a temperature increase of 20 degrees? 30 centimeters, which is a lot. Gosh, man, that's an awful lot. It would be 30 centimeters. That's a third of a meter. That's like a foot. So you can see why you have expansion joints in bridges. So excellent example of civil engineering and coefficient of linear expansion. Excellent problem. A cook pours 1 liter of ice water at 0 degrees Celsius into a pan of hot water at 80 degrees Celsius and finds that the mixture reaches a temperature of 60 degrees Celsius. How much hot water was in the pan? Heat lost by the hot water is gained by the ice water. Since 20 degrees Celsius change of temperature of the hot water is only 1/3 as much as a change of the temperature of the cold water, there must be 3 times the mass of hot water. Therefore, the pan contained 3 liters of hot water. Again, if you have a problem with that, you might want to just make up some numbers to see if, 1 liter is 1,000 grams using the specific heat capacities. That might be a way to do it. Might make things a little clearer. Your perfectly insulated bathtub has 82 liters of water in it, but it has cooled down to a temperature of 39 degrees Celsius. You'd like to add just the right amount of 50 degrees Celsius water to the tub to make your bath water the perfect temperature of 42 degrees Celsius. Show that adding 31 liters of 50 degrees Celsius water to the tub will accomplish this. So plug into everything. The specific heat capacities are going to cancel, and that's it. So just solve for the mass of the hot water. And on the next slide, you'll have it continued. So here we're solving for the mass of the hot water. And now plug in for the mass of the hot water. It's going to be 31 kilograms. 1 kilogram is 1 liter. So 31 kilograms is 31 liters. So show that adding 31 liters of 50 degree water to the tub will accomplish this goal, and it does accomplish the goal. So sometimes it's important to show, to write the, solve for the equation before you do the calculation. Sometimes that's very helpful.